Hello and welcome to my presentation. My name is Florian Arbeiter from the University of Leoben, and today I would like to talk to you about the damage tolerance and fracture properties in fused filament fabrication with regard to current trends, limitations, and also the possibilities. Now, fused filament fabrication, or known under fused deposition modeling, fused layer modeling, material extrusion, and so on, is actually quite a simple process, which is basically using a polymeric thermoplastic filament, pushing it through a heating block into a nozzle, and the whole thing travels along a predefined path in a, for example, G-code, and deposits the material so that your specimen or component actually is being produced in a layer by layer fashion. Now, the first trend I would say in fused filament fabrication was actually regarding the machine and the parameters which you can play around with in fused filament fabrication. And there was a lot of empirical testing, so basically printing specimens with different parameters and having a look at the subsequent parameters of the specimens or the components. For example, if you have a look in Scopus and punch in just fused filament fabrication properties and strength, you find close to 900 documents which deal with this topic. And as I've shown you before, there are quite a few different names under which you can find this technique. So I would expect a few thousand documents actually which deal with the empirical testing and optimization of parameters. Now, this optimization of machine parameters is usually done, or was usually done, via design of experiments and subsequent statistical analysis, as shown here, for example, with a surface response methodology, where you test a lot of different parameters, have a look at the resulting properties, and then try to find the optimum parameters with this statistical analysis. So basically it was understanding the machine and the processing parameters and what this does to our final properties. However, I would say now there is a shift towards understanding the actual underlying reasons of the resulting properties of the polymeric materials. And these underlying reasons can, for example, be categorized in these four subcategories. Of course, one big influence is the chosen material. The first studies were usually all done either on PLA or ABS, but of course there are a lot of different thermoplastic materials out there with different and interesting properties which you could use to actually tailor your final properties. And of course, there's the diffusion and entanglement processes which occur at the interfaces of the different deposited strands, which is also quite a significant factor with regard to the final properties. Have a look at voids, defects, cracks, notches, and so on, as shown here, for example, for small tensile bars, which were examined using micro-CT analysis. Of course, the actual loading condition with regard to the layer orientation can be quite impactful because, for example, as shown here, if you have plus minus 45 degree printing orientation, you can also get a mixed mode loading of the interfaces between the strands, which can significantly influence your properties. Also quite important for polymers is, of course, the strain rate dependent material properties, which have been mostly neglected, I would say, so far, because most studies you can find are actually on quasi-static testing results. Sometimes we have impact loads if, for example, Charpy tests or ISO tests were performed, but usually for engineering applications, we would have to have a look at the actual strain rate dependent material properties and also, of course, creep or creep rupture and fatigue properties, because they can be quite significant for some materials and not so much for others. For example, shown here for strain rate dependent testing between 10 by the power of -3 to 10 by the power of 3 millimeters per second. For tensile tests on peak, we can see here we have a slight change in properties, but it's actually not too much. But for example, on PVDF here, or similar it would be for polypropylene, for example, we have quite a drastic change in properties depending on the applied loading rate. And also quite important, of course, would be the fatigue behavior of our printed specimens. Fatigue is usually one or the most detrimental loading that engineering applications undergo, and it is quite sensitive to pre-existing notches. For example, as shown here for a 3D printed wrench, which is then cyclically loaded, we can see a crack starting to grow at one small notch in the beginning, and the crack starts to accelerate through the whole wrench until a final failure occurs and the wrench is not operable anymore. So the question is, of course, if we want to use 3D printed polymeric parts in actual engineering applications, what about our lifetime estimation? Can we estimate a lifetime so we can ensure a safe application of our components? And for the determination of lifetime, we have different possibilities. One would be we can, for example, use fracture mechanics lifetime estimation. On the other hand, we could also use a damage accumulation based lifetime estimation. So this would be based on, for example, stress or strain based Wöhler lines. And it depends on actually how your material behaves during its lifetime. And as we have seen with the wrench before, we actually have a singular crack which is dominant and then subsequently grows through our component. So for this study, we focused on a fracture mechanical approach. Fracture mechanical approach basically is a combination of experimental testing, so we can get our crack growth kinetics of our material and some usually numerical or analytical estimations of the local stress intensity factor in our component as soon as the crack length changes, so the crack starts to grow. So in detail, for example, if the material is near homogeneous, as it was the case with our printed wrench, because it was printed from PLA, which is quite easy to print, also to get it almost homogeneous in its final properties, we could use an approach based on linear elastic fracture mechanics. For example, we determined the crack growth kinetics, as shown here in this picture, which were actually quite nice, I would say. In the next step, we had a look at the geometry and performed finite element analysis to get the local stress intensity factor at different positions when the crack starts to grow. It looks something like this. So we got the stress intensity factor K1 max, so at the maximum applied force during a cycle, as a function of the crack length as soon as the crack starts to grow. And in the end, we did some validation with experiments. So we had a look at real printed wrenches, loaded them cyclically, as shown in the video before, at different loading forces, and compared the results shown here in the green circles with the finite element analysis and fracture mechanical lifetime approach, as shown here in the dashed and full lines. And as we can see, for one printing orientation, we could actually get quite nice agreement between the estimated results via fracture mechanical analysis with the actual validation experiments. So one problem, of course, is this only works as long as the material is quite homogeneous and we can apply this fracture mechanical approach, which is then using one dominant crack to estimate the lifetime. Crack growth, if the material is not homogeneous, as shown in this previous study, can get very complicated, as shown in the picture here. For example, for a different printed material, where the crack should grow perpendicular to the deposition orientation. And depending on the applied load, we can see that we have here a competition, for example, between crack penetration and crack deflection. And this can lead to quite different results. For example, shown here in the graph on the bottom right, we have a crack growing parallel to the printing orientation with a material which is not easily printable, I would say. So the diffusion at the interfaces between the deposited strands is not very good. And here we can see that actually the crack grows in a quite nice crack growth kinetic. Regardless of the starting value, we always reach the same crack growth kinetic power law, and the crack grows through the material quite easily. On the other hand, shown in the left region of the graph, we can see if the crack grows perpendicular to the printing orientation, we again get a quite complicated crack growth and crack advancement because we have this competition between crack deflection and crack penetration. And for example, for higher loading levels, indicated here in red, green, blue, and black, we still get some sort of crack propagation across the different strands. But as soon as we reach a certain level, we get actually this gray cloud of data points where actually there's not really a crack growing. So this makes it quite complicated, of course, to use fracture mechanics based lifetime estimation. In this case, if it behaves like this, it would be beneficial to change to a different approach. For example, as I said before, damage accumulation based lifetime estimation would probably yield better results, but there's only few, I would say, good studies available in literature. So there's quite a lot of work to be done in this area, I would say. However, the use of these weak interfaces can also be seen as a possibility. Because if we have weak interfaces, of course, this leads to deflection, as discussed previously. And this actually hinders, or can in some cases even stop, a crack from growing any further. And this could, for example, also be used to increase the toughness or the lifetime, the fatigue lifetime of a specimen much more than actually printing the specimen even better. As now shown here in purple, as I said before, this was an experiment done at rather low loading levels. And here the crack actually started to deflect, as shown in the picture on the top right. And this actually stopped the crack from propagating further through the whole specimen. And this way, the test actually lasted for a few million cycles before we actually stopped the test because it did not fracture, compared to the tests shown in the other colors, which lasted only a few tens of thousands or hundreds of thousands of cycles before the specimen actually broke because the crack propagated through the whole specimen. So this could be used as an advancement. However, it is quite difficult to get the exact right, I would say, interface toughness to promote this type of failure without them delaminating in an uncontrollable way. So there's a quite precise control necessary if you want to do it like this. A different possibility to increase the damage tolerance would, for example, be the use of a soft material sometimes in between the different other material layers. Because this is also shown to be able to stop the cracks quite nicely without having to have this very exact and precise control during the processing of the specimens to tailor your interfaces with the weakness based on the diffusion. And for example, we see here on an impact testing where we included very soft TPC layers in a PET-G material, where actually the impact toughness increased by a few 100% just by using this soft interlayer in between. Or as shown here in the pictures, we actually used a few different configurations with a different number and thickness of soft layers, but actually it was shown that if you use just a single layer, it's usually also enough to stop the crack from propagating further. So, however, we have of course some cost because this is highly depending on the loading condition, and we also lose a certain amount of stiffness if we include these soft interlayers. And furthermore, it's of course depending on the exact loading speed, the loading direction, and so on. But this could be a nice way to further increase toughness. So to conclude, we have many unsolved issues regarding the mechanical properties of materials or specimens produced by FFF, especially with regard to non-quasi-static loading conditions. We don't actually know that much about our materials yet. Specific layer architecture with either weak interfaces or soft interlayers can be used to increase the damage tolerance, which is quite nice, but we have to put in a bit more work there to actually understand when and how we can use it. And yeah, as I said before, this only works if the interfaces are tailored correctly. So with this, I would like to thank you all for your attention. And if you have any questions, please feel free to contact me at the shown email address. And with this, I would like to thank you again for your attention and of course also our funding agencies.